So now ordinary least, how do ordinary least squares work? Okay, how do we obtain the estimates? By using ordinary least squares. Let's look at the logic of ordinary least squares. Okay, now we know that y is equal to, we write model as y is equal to a plus bx plus e. Okay, which means that the predicted value of y is equal to a plus bx. Right? Predicted value of y is a plus bx. Now, so the error actually is y minus y prime. That is the actual value of y minus the predicted value of y. Okay? Which means error is equal to y minus a plus bx. Right? Now, if this is the error, then what, or residual of prediction, then how do we estimate b so that we keep these assumptions, we follow these assumptions, and the OLS says that, the OLS estimator says that for each observation we can get E, because for each set of observations we'll have a y and a x. So similarly we'll have a y predicted, which is a plus bx, right? So I'll have a and b, and I multiply x by b and add a into it, I get y prime values. They are not values of y. Okay, so suppose my model predicts y to be 4. Actually the value of y is 5. So the difference between 5 and 4, that is -1, is error. Now some differences will be positive, some differences would be negative. So if I sum the differences, the sum of the differences is going to be 0. Okay, that's what I said, that one of the assumption was it's normally distributed with mean 0, variance 1. Right, so mean will be 0. So what I do is I do the square of E and then I sum the square, so I get a sigma E square. Okay, the sigma E square is minimum. So B is that value for which sigma E square is the smallest value. Okay, you put any other value other than the value of B estimated by OLS, then the sigma E square will be larger than this value, than the sigma E square for this value. Okay, so B is found out in such a way, B is obtained in such a way that summation E square remains smallest for that particular B. You write any other value of B, sigma E square cannot be smaller than the sigma E square that we get when B is estimated by OLS. So OLS uses this logic. The logic of OLS is to keep sigma E square smallest. Logic of OLS is to keep the sigma E square smallest. Okay, and so by keeping this in mind, the B has been computed. Okay, now we know that I can erase this. Yes. Now, how do I do this? Okay, we know that covariance xy is equal to summation I is equal to 1 to n x minus x bar y minus y bar upon n minus 1. Okay. Now B is, or generally you write dyx, B is covariance xy upon variance of x, covariance xy upon variance of x. Okay, so we know how do we get covariance xy, we know how do we get variance of x. So variance of x is equal to summation I is equal to 1 to n x minus x bar bracket square upon n minus 1 is the variance of x. So I can actually write, if I have to write everything as in one formula, then I can write byx is equal to summation I is equal to 1 to n x minus x bar y minus y bar upon n minus 1 upon summation I is equal to 1 to n x minus x bar bracket square upon n minus 1, right? And so I have what remains then is just the numerators of both, that is summation x minus x bar y minus y bar upon summation x minus x bar bracket square. So I would get rid of the two n minus 1s, and so basically this is what the formula then can come to, right? So I'll have only this would reduce to summation I is equal to 1 to n x minus x bar y minus y bar upon summation I is equal to 1 to n x minus x bar bracket square, right? This is what the formula there would be. The easiest thing to remember is covariance xy upon variance of x. Now, given this, I can write, given this, I can write that I know that y is equal to, y bar is equal to a plus bx bar, right? I know that y bar is equal to a plus bx bar. Okay. Y bar is equal to a plus bx bar. So I can actually have y bar minus bx bar is equal to a, right? So if I want to compute a, the a computation is very straightforward. A is equal to y bar minus bx bar, right? And I get a. Once I compute a and b, then my regression equation is set.